So let us start the explanation part of deletion theorem. The statement says if a non-null vector space V over F be spanned by a linearly dependent set. Non-null vector space means this V not only contains the null vector theta, but something more to it. Because if the vector space contains only theta, then there is nothing to prove. So that's why it is a non-null vector space V over F spanned by a linearly dependent set S is equal to alpha 1, alpha 2, dot 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 alpha n. This set is linearly dependent. Linearly dependent means this concept means if you choose linearly dependent, this concept means if you choose few scalars c1, c2, dot dot cn and consider this combination c1 alpha 1 plus c2 alpha 2 plus dot dot cn alpha n is equal to theta, then at least one of the scalar must be non-zero. Linearly dependent means if you choose few scalars c1, c2, cn and choose the and take this combination c1 alpha 1, c2 alpha and cn alpha n equal to theta, and if this implies at least one of the scalar is equal to is non-zero, then we call it is a linearly dependent set. And if all of the scalars are zero, then it is implied it is a linearly independent set. Linearly independent dependence, this concept is very much used in the concept of basis. Now let us come back to the theorem. If a non-null vector space V over F be spanned by a linearly dependent set S, spanned means L of this set is equal to total vector space V. Span means L of this total set is equal to this vector space V. If V is spanned by this set S, then V is also spanned by a suitable proper subset of S. That is, if we delete, let's say, one vector from this set, or let's say two vectors from this set, then there is nothing change of this spanning part. That means if there are n number of vectors in S, and if we delete one or let's say two, then that remaining n minus 2 number of vectors also span the same vector space V. This is called deletion theorem. That means deleting one or two vector will not hamper the spanning part of that set, spanning part of that vector space. Now let us come to proof. Since S is linearly dependent set, at least one of the vectors of S, say alpha j, can be expressed in this way. Because since it is a linearly dependent set, so at least one of the scalar, why is it so? Let me calculate over here. Suppose this is the linear combination C1, C2 alpha 2 plus dot dot Cn alpha n equal to theta. Now, let's say if it is linearly dependent, then at least one scalar is non-zero. Let's say Cj not equal to 0. So C1 alpha 1 plus C2 alpha 2 plus dot 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 dot, dot plus this, let's say Cj alpha j plus Cj plus 1 alpha j plus 1 plus continuation Cn alpha n equal to theta. As we know, this Cj is not equal to 0. As we know, this Cj is not equal to 0. So therefore we can take Cj alpha j one side and changing the side for the other scalars C1 alpha 1 minus C2 alpha 2 minus dot 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 minus Cj minus 1 alpha j minus 1 minus Cj plus 1 alpha j plus 1 minus dot 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 minus Cn alpha n. Since Cj not equal to 0, so it inverse must exist. It inverse exist means we can apply Cj inverse both side. So it will be minus Cj inverse C1 alpha 1 minus Cj inverse C2 alpha 2 continuation minus Cj inverse Cj minus 1 alpha j minus 1 minus dot 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 minus Cj inverse Cn alpha n. So this become alpha j, and this we can consider as a d1. Let's say d1 alpha 1. This total minus part is d1. Then next is d2. In this way, we can consider dj minus 1 alpha j minus 1 plus dot 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 dn alpha n. Clear? So this is the explanation of this line. This is the explanation of this line. Since it is linearly dependent, we can express alpha j in this way. Since it is linearly dependent, otherwise not. Where di is a scalar, I equal to, as I told you, this I runs from 1 to j minus 1, and after j minus 1 it will be j plus 1. It will be j plus 1. After j minus 1 it will be j plus 1. So this is the explanation. This is the range of I. Now here S is this set and it span the whole vector space V. That's why LS equal to V. Now let T equal to alpha 1, alpha 2, alpha j minus 1. That means T in the set T, one vector is missing. What is that? That is alpha j. In S, all the vectors are present. In T, one vector is missing. That is called alpha j. Now, as you know, T contains less vectors than S. So T subset of S. This implies L of T subset of L of S. Again, L of T subset of L of S. Because of this, again, since every vector of S can be expressed as a linear combination of vector T, we can say LS subset of LT from this. From 1, we can say LS subset of LT. Why? Because a vector of S expressed as a linear combination of vector of T. That's why LS subset of LT. This part is very simple. Since T is a subset of S, so LT subset of LS. As simple as that. And for this, the reverse part, use this in equation. Since alpha j is a member of S and it can be expressed as a members of T, so L of S is a subset of L of T. When we say L of S subset of L of T, this you can say in two cases. At first, case 1, if S subset of T, then LS subset of LT, as simple as that. Case 2, if a vector of S is a linear combination of vector of T, then also you can say LS subset of LT. Clear? If S subset of T, then this will hold. If a vector of S is a linear combination of vectors of T, then also this will hold. So LT subset of LS and again LS subset of LT, these two together imply LS equal to LT equal to, as you know, LS span V, and since LS equal to LT, so LT also span V. Now you tell me, T is smaller than S, one vector is deleted from S to construct T. I constructed T after deleting alpha j from S. That means the statement of the deletion theorem holds, because deleting one vector of S also remains the spanning concept. So this is the explanation of deletion theorem. Now let us come to the next thing. Basis of a vector space. Basis of a vector space. Let V be a vector space over a field F. A set S of vectors in V is said to be a basis of V. As simple as that, V is just a vector space over a field F. Let us consider a few vectors from V, and that will form a basis if first S is linearly independent in V, second S span or let's say generates V. That means these two conditions togetherly imply it is a basis. The first one is linearly independent, second one is LS equal to V. This is the definition for a basis. If one of them fails to satisfy, then it will not a basis. First is S is linearly independent, second is S must generates V. Now, there is an important theorem, existential theorem, which states that for every finitely generated vector space, we must exist a basis. We must have a basis. What do you mean by finitely generated vector space? It means the vector space V must generate by a set S which contains finite number of vectors. It means the vector space V must generated by a set S which contains finite number of vectors. If this happen, if the vector space V is generated by a finite set of vectors S, then there must exist a basis for that. For infinitely generated vector space, we can't say like this, but for finitely generated vector space, there must exist a basis. Now, the proving part. Case 1, let V be a finitely generated vector space other than the null space. I am not considering the null space. I am considering it is a vector space other than the null space. And the set S contains n vectors alpha 1, alpha 2, alpha n, which generates V. If S is linearly independent in V, then S itself a basis of V. If S is linear, look, I told, as I said, it is a generator. This finite set is a generator of V. That means second condition is already assumed. So if this set is linearly independent, then it is a basis and the theorem is done. If it is dependent, then by deletion theorem we can delete one vector from S and at least one vector from S, because as you know, using deletion theorem we can delete one vector from the set and that will still remain the spanning set. So after deletion we'll get S1 which will span the space V. So again the second condition satisfied. Now if this S1 is independent, then again the theorem is done because it is a basis. If S1 is linearly independent, if this is independent, then it is a basis because it spans the set. Otherwise, if it is dependent, then again we repeat the process of deletion. But since it is a finite set, we can't delete infinite number of times. So at the end, we will get a set which spans V and which contains one vector and which is linearly independent. You got my point. The point is, suppose you have alpha 1, alpha 2, dot 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 alpha n. This set generates V. Assume it. So second condition done. For the first, we need an independent part. Let's say it is not independent. So it is dependent. So delete it. You get this. It will still span V because deletion theorem. If it is independent, done. If not, delete it. You will get another set of vectors that will span V by deletion theorem. If that is independent, done. Otherwise, delete it. Proceeding in this way, at the end, how many vectors remain? Only one, because you can't delete only one vector also, because in that case it will become a null vector space. So at the end, you will remain one vector. You will have one vector in your hand, so that will obviously independent. মানে আমি বলতে যাচ্ছি তোমাদের কাছে ধরো n সংখ্যক ভেক্টর আছে, তুমি প্রথমে কি করলে, প্রথমে একটা ডিলিট করলে করার পর স্প্যান থাকলো, দেখবে ইন্ডিপেন্ডেন্ট হয় কিনা, যদি হলো তো ভালো, তাহলে শেষ, যদি না হয় আরেকটা ডিলিট করলে, আবার ডিপেন্ডেন্ট পেলে, যদি ইন্ডিপেন্ডেন্ট হয় ডান, যদি ইন্ডিপেন্ডেন্ট হয় আবার ডিলিট করো, এই করতে 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 লাস্টে কি হবে, লাস্টে একটা থাকবে তোমার হাতে, কেন কি এটা ফাইনাইট সেট, আর যখন একটা থাকবে, একটা তো সবসময় ইন্ডিপেন্ডেন্ট হয়, তার মানে কি তুমি পেয়ে গেলে যে তোমার একটা বেসিস থাকছেই ফাইনাইটের ক্ষেত্রে। এটাই ফাইনাইটের ক্ষেত্রে সুবিধা যে ডিলিট করতে করতে শেষে গিয়ে তোমার হাতে একটাই ভেক্টর পড়ে থাকে, এর থেকে কম হতে পারে না, কারণ কি আমি প্রথমেই ধরে নিয়েছি যে এটা হচ্ছে একটা ভেক্টর স্পেস আদার দেন দ্য নাল স্পেস। নাও কেস 2, if V contains only null vector, then it is very easy. Null vector is generated by the empty set phi and it is a basis. It is very easy. Now, I have to stop here because of the less of data. I will upload a video regarding replacement theorem and dimension and existential theorem tomorrow. Thank you.